Hello, everybody. Welcome back to our NSX 4.0 tutorial. In today's lesson, we're gonna continue on where we left off, which is we're talking about a multi-tier routing in this lesson. Let's get right to it. So in the last class, we talk about single tier. So that means we have only one tier of the routing function of our networking, which T0, we call it T0 routing, like this T0 logical router. So in the multi-tier, we talk about two tiers of routing, which is in which we have a tier 0 logical router, which is a relatively large and kind of like aggregation point of the whole NSX routing. And we also have another layer, which is called tier 1 logical router. You can see, you can call it access router when you compare to physical world. So we have two tiers. One tier is T0. One tier is tier 1. So how do we leverage multi-tier or two-tier NSX topology? So for tier 1 logical router, we can leverage tier 1 concept for creating multiple tenants, or let's say there's a big enterprise and there are so many departments, so we can create individual tier 1 for every department, or just you can say this, it is a different tenant what different department uses. That's what a tier 1 is all about. So for different tenants, so there's a flexibility for you to create different tenants. For example, when we look at the creation of tenants, the tenants, firstly, we just separate the tenants into the isolated part, networking part. Secondly, we have when we think about tenants is always dependent with their own physical network. How do we understand that? Just for example, there's two tenants, green one and the yellow one, and in this tenants diagram, or just topology, you can have this topology with the same subnets with the yellow one. That means tenants networking is independent to one another. That means if you have 192.168.0.0/16, for yellow tenant, you can have the same range of IP address, 0.0/16. So IP subnets are overlapping. That's the key. So we say it is dependent to each other. So another perspective of looking at multi-tier, that means if you look at tier 1, tier 0 logical router, tier 0 logical router means tier 0 always connects to the physical router. Yeah, now then the tier 1 is always connected to your production VMs. That's the what this topology looks like. Okay, let's move on to some of the terminology of multi-tier. So as you have seen, we have some interface types and also corresponding terminology for this. For example, uplink. Uplink means when you look at T0, uplink means this link or this interface, or router link means interconnect between T1 and T0. So that's a router link, which is internal link. So you don't care about a mechanism from T1 to T0. So everything is taken care of by NSX. So we have downlink. Downlink means down to every segment or VMs. So for a router, no matter it is T1 or T0, there's a routing table. So there's some route types, for example, static or direct connected, and also have some of the dynamic or OSPF learn or BGP learn. So that's pretty same as a physical routers. So we talk about multi-tier DR, distributed routing, because in the last lesson we talk about LR. We talk about LR. LR consists of SR and the DR, two parts. So for two-tier topology, we also have a DR and SR. That means T0 has its own DR and SR. T1 also has their own DR and SR parts. So let's dive into this to see how two-tier DR works. So when you deployed a two-tier NSX, so DR function will be sitting in every node on every node. So T0 has their own DR and T1 has its own DR. So in this ESSI-1 host, we have 3 DR belonging to different routers. So let's say we have a blue VM, we have a yellow VM, they want to talk with each other. So how do we leverage 3DR to do the routing function? So here, this is a routing path. So that means that when VM sends out the packet, they go through the tier 1 DR, which is this own default gateway, and then go through the interconnection between a T0 and T1 and T0, and T0 will route this packet to another T1, which is yellow T1. Then in turn, T1 will do the final step or final routing to the destination. So that's the 3 DRs in between the whole communication. So the next day, the yellow VM goes to a migrating to the ESSi2 host. So the traffic will change to this because remember I told you two rule of thumb, and so when the packet sends out and it goes to different DR function, routing function, and routing always happen firstly, or routing happens earlier than switching because, for example, this is 3 routings have been finished before switching. Switching in NSX means there's a tunnel encapsulation, Geneva tunnel encapsulation, and then the packet will go to another transport node via this Geneva tunnel. So we can see that demonstrating this rule, the routing happens first, then switching. In another direction, the same thing happens. Routing happens earlier than switching. So they use the closest routers for routing function. Then the last step is tunnel encapsulation or switching to the final destination, which is blue VM. So you can see that they are two different paths, forwarding paths for the inter-tenant traffic that representing these two rules. Routing happens earlier than switching, and routing happens as close as possible. So that means when you choose DR function where the closest DR always been chosen for traffic forwarding. So routing happens as close as possible, close with regard to the source or just source or with regard to the packet. And let's walk you through the whole forwarding path, which is under 2 tiers topology. And this is for outbound traffic. That means there's a VM wants to talk to the outside PC, which is 192.168.10.1. So source will be the 10.1.1.10, and the destination will be 192.168. So it is outbound traffic. Oh, sorry about that. And firstly, the payload just gets sent out to their to their gateway, which is the closest DR, because this VM is setting on this TN, right? So they are some DR, T0 DR, and T1 DR setting on this transport node. So for the first step, VM send out, this VM send out some packets to their gateway, which is T1DR. This is a gateway right here. And the T1DR will check this routing table. Oh, sorry. Checking this routing table to decide the next hop, which is T0DR. So next hop will be T0DR via what interface? Via this yellow interface to T0DR, right? The next step for T0DR will check their routing table to see to see the next hop, which is T0SR. So T0DR will send the packet to T0SR, which is here via this transit segment to T0SR interface right here. And T0SR will check this on routing table and send out the packet out to the physical router here. And physical router in turn to route this packet. That's the outbound traffic. So you can see the whole source destination path will be VM T1DR yellow one and the T0DR, T0SR, then physical router and outside. This is the whole forwarding path. And for inbound traffic, let's look at the inbound traffic. So packets or payload get sent out to the physical router then give this packet to T0SR. So T0SR is the first step within or in terms of NSX system or within NSX system. So T0SR will check their routing table to see the next hop, which is T0DR, which is the closest DR to the T0SR, right? So remember that rules. When you try to decide the next hop, always choose the closest one. So T0DR will be, in this case, will be chosen. So the packet goes via this link to T0DR function. Then the T0DR will go, the packet will go to the T1DR, which again closest the DR, right? T0DR, because T1DR, all three routers are setting in the same transport node, which is edge node, which is this transport node. Then T1DR just check the final step, which is direct connected subnet, because this dark blue link is direct connected in terms of in regards to this VM. So this is the last hop for routing function. But if you notice that this is a cross transport node traffic, so for the last step, forwarding, the tunnel encapsulation or Geneve tunnel encapsulation will be used for the final step. Yeah, that's the inbound traffic. The whole path will be outside T0S1, T0DR, T0SR, T0DR, and T1DR and VM. So if you compare outbound traffic and inbound traffic, definitely they are different paths because the two rules applies to the whole process. So you just, the choosing of DR and, the first routing is always earlier than switching. So always remember these two, those two rules for the forwarding path decision. So here's a summary for T1, T0, and an SR. Sorry about that. And just remember that T0 has their own SRDR, T1 also has their SRDR. So when let's say we have two-tier topology, so there's a diagram for the SRDR distribution. So T1 at the bottom and the T0 at the top. So from this VM to physical router, we have to go through 4 routing function for 4 router, which is DR, SR, DR, SR. That's the critical things for you to remember. And also have some the interconnection, SR, DR interconnection, or in router link. Those are internal links, so you don't care about that. Just, the subnet IP address will be allocated automatically by NSX itself. So another one I want to mention is this one, centralized services port. This is a pretty old school term. Right now we have service interface port. Service interface port is equal to CSP. This labeled 5 right here. So for a T0, you can attach a subnet or segment to a T0. And what's the difference between service interface and the downlink interface right here? Downlink interface always meant to the points to overlay subnets, and service interface points to VLAN-based subnet or VLAN-based segment. So, for example, you have an existing VLAN subnet, and running in your data center. So you want to move this VLAN gateway to NSX system. So you move your previous gateway from the physical router to the T0 system. So in this case, this VLAN gateway or this interface for this VLAN gateway is called service interface. Service interface. That's what service interface is all about. It's just a VLAN-based gateway. You can attach service interface onto T0. You can attach service interface onto T1. Both are correct. Let's move on to edge node. So In the previous lesson, we talked about T0, Tier 1, and logical router, but T0, T0 and Tier 1 routers are always setting on the edge node, which is a VM or bare metal. So in this slide, I meant to give you a little bit concept about traffic distribution. Don't worry about the other aspects. We're gonna go through this. We're gonna get into it later in the chapter. So I just want you to notice that if how we allocate or how we locate our T0 or T1. So T0 or T1 are setting on the edge node VM, right? So edge node VM, when you look at the edge node VM has its own switch, NVDS switch. You can have one, you can have two, or more than two. It's okay, but generally, here there's a one NVDS for this edge node VM. So in this for this edge node, we have 4 fixed virtual NIC. This is virtual NIC 4. So 1 is for management IP, 2, 3 is for VNIC 2 and VNIC 3 for traffic. I mean traffic which that includes overlay traffic or TCP or IP tunnel traffic and uplink traffic. VNIC 4 is for bridging function, so you don't. Now just skip the bridging function here. And upwards a little bit, we have the correlation of tunnel trunk pro group and the VNIC. So here's a relationship or connection between the uplink VDS pro group and fixed VNIC 2 or edge node VNIC. So this connection we can create this connection. We can manipulate this connection. For example, in this connection, we allow VLAN 300 for uplink VLAN and uplink traffic. We allow VLAN 200 for overlay traffic. So from this interface point of view, there are 2 VLANs or two types of traffic are going through or traversing. And for this interface, VNIC 3, we have another VLAN 400 and also VLAN 200 to the other 2 VLANs. So that means we just go up a bit. We have a physical NIC. We have a VDS, right? So that means how we distribute our trunk port group traffic to physical uplink. This is a real physical uplink. There also the connection distribution mechanism. So from this diagram or from this slides, we can learn that there are different layers of traffic distribution. So we can manipulate manually. So that means we have a very flexible mechanism for edge node to manipulate the traffic via different layers. For example, this layer, this is first layer, this is second layer, third layer, and also have some, remember the uplink profile is also another layer for distribution, traffic distribution. So as said before, we can leverage named teaming policy, this feature for you to manipulate or for you to create this kind of correlation. For example, we have overlay, which is load balance for red traffic. We have load balance between VNIC 2 and VNIC 3. We also have two named teaming policies for VLAN 300 and for VLAN 400. VLAN 300 and VLAN 400 are two VLAN-based uplinks. So you can set. So that means that with this configuration, you can create this structure. So for you to manipulate the traffic or for you to distribute the traffic. That's it. So we'll talk about this or get into detail for edge node in the later chapter. So no worry about that if you don't get through to it. If you don't get it across. So let's talk about edge cluster now. So we talk about edge node. So edge node is a separate VM. So you can put edge node onto different ESXi hosts for physical redundancy, right? So there's also a structure called the edge cluster. So we can put at most 10 edge nodes in a cluster. That means in this cluster, we have at most 10 edge nodes for you to control the whole edge node function, for kind of like an aggregation concept for the edge nodes. So in every edge node, you can deploy different logical routers or different logical router function or modules. So there are two types of design for allocation your logical router onto edge node, then onto edge node cluster. For example, here we create edge node cluster 1 consisting of 4 edge node, right? Edge node. So we put this function 0. Oh, sorry. We put tier 0. We put tier 0 for tier 0 to all the edge nodes, right? That means we create tier 0, but this tier 0 has 4 copies. So we can put tier 0 onto every node. We can also put tier 1 function with load balancing function here onto different edge node. No, please note that just tier 1, this is a active tier 1 function. This is a little bit grayed out is standby function, standby tier 1 router. So tier is another pair, tier 1 is active. It's a standby. Standby always grayed out, shown in the picture. So that means you can create a very big cluster, and you can put all of your edges, edge nodes into this cluster. This is design one. We also have design two. So we create two cluster with two edge node each. So for this cluster, for cluster one, we put tier 0 function in it. And for this, we put tier 1 function or tier 1 router for this cluster. So we just separate the functions or separate the router groups onto different clusters. This is design, second design. Yeah. Please notice that if you put tier 1, only one tier, if you put tier 0, only one tier 0 should be put on the edge node. But when it comes to tier 1, you can, so a edge node can hold more than one tier 1 routers. But for tier 0, just hold only one. Let's talk about HA, high availability, because we already mentioned that. So when we talk about high availability, we talk about logical routers high availability, not talking about high availability of the edge node. So for edge node, we have a cluster, we have multiple edge nodes within the cluster. But when we talk about high availability, we talk about the tier 0, tier 1's HA. So please notice that this is a confusing one. So for every logical router, we have two HA model. We have active, we have active standby. For tier 1, for tier 0, we only have active, and we also have active standby. So that means for tier 0, when you assign tier 0 to the edge node, we can configure, or we can create this pair of tier 0 with AA model. That means both tier 0 routers are working at the same time for packet forwarding. But for tier 1 only has active standby mode. That means you can allocate tier 0, tier 1, but only one tier 1 is active. Another tier 1 is a standby mode. That's the restriction, or please remember that when, especially for the exam, tier 1 has AA and AS mode. A tier 0 had this AA and AS mode. Tier 1 only has AS mode. So for when we look at tier 0, if you put them for in the AA mode, or active mode, there's something I want to mention, that there might be a symmetric routing. So that means we have to manually maintain the stateful table, manually maintain the states. For example, there's a stateful services, which is a firewall. Firewall has session table. If you put this firewall, stateful firewall, onto active mode, it doesn't work, because traffic goes out from via this T1 SR. The reply traffic will go through another T0 SR. That means there's any session table here, so every reply traffic will be blocked. That means you have to manually maintain your states when T0 is in AA mode. So if you have some of the stateful services, for example, SNAT or DNAT or translation table or load balancing, firewall, or some of the VPN has a need to have states, the only choice you have to choose is tier 0 active standby mode. If you don't have any stateful services, you can put them into active mode. So that means you tolerate asymmetric routing. That's a HA. That's a HA concept for tier 0 and tier 1. Tier 0 and tier 1. Yeah. Especially for SR, because SR is centralized points when it comes to HA. DR, there's nothing to do with DR, because DR is distributed. So that shows the traffic going out from this SR, and when something happened or this tier 0 SR failed, a traffic will goes to a failover to another one. But if it's AS, oh sorry, just I got it. I messed up. The previous one is AA. So it's AA. AA means traffic goes this way. At the same time, traffic will go this way at the same time, because this active mode. But when it comes to standby mode, where we set it as a active standby mode, we only have one way, or only have one path working, and only if the failed standby tier 0 SR will work. Yeah, this is everything for today's lesson. Hope you enjoy it, and just like it and share with your friends, and leave some comment and question, and I'll answer them. Thank you so much. Have a nice one.